Okay, so now that we know what this stuff is, what do we do with it? How do we, more importantly, how do we program for it? As, again, as an OS designer, as a file system designer, as an application designer, how can we access this stuff? Right, so one thing the SNIA is doing is we are rallying a lot of the industry around this point of view that's very application-centric. So we're kind of starting from the top down as opposed to bottom up. This is an interesting thing, right? And we have published a programming model. It's currently version 1.1. And again, you can access this from the SNIA website. Now, version 1.2 is in the final stages of the approval process. So even though it's 1.1 today, it will shortly be 1.2. That's a little trailer for you, if you like. So SNIA.org/PM, you'll be able to see fairly soon. I would say within a couple of months, if not before. But again, very vendor neutral. We don't call out products. This is a programming model. This is a how-to. You may have heard the little tease on Twitter that this is the cookbook. So behold the cookbook, right? You want recipes for persistent memory? Use the cookbook. It's a great thing. So we wanted to do two things with this model, right? We wanted to accelerate the availability of software, helping the industry, helping the companies that belong to the SNIA and the individuals that want to use this model, right, to develop their software. And the hardware can include both SSDs, again, disk storage semantics using non-volatile memory. NAND is an example of that, although there are others. And then persistent memory, which is byte addressable. So the software we envision spans the range, starting from applications all the way down into the deep layers of the OS. Right? So we created this programming model, and it describes behaviors. That's one thing it does. Right? How does this stuff behave? We want to describe that up to the application so the application programmer can know how to access it correctly. So this is, now one thing, this is not an API. So if you open this document expecting an API, that's not it. This is a programming model. If you're a programmer writing code, you would use this perhaps to create an API for your application or for your file system or for your OS, right? And then it also exposes the opportunities if you're doing embedded type programming with networks and processors, things like that. It also exposes how this stuff behaves. So again, it's modeling behavior. And then, of course, how to use it. So again, the 1.1 version is a little more than 2 years old now. And it does expose new block and file features, again, in the storage semantic sense, to applications. And in particular, because, again, this sits in a memory channel, right? The atomicity capability, in other words, being how do you do an atomic operation to persistent memory, right? We have learned how to do this for disks, right? Rotating media, solid state media, things like that, right? But how do you do that to memory, right? Well, with DRAM, it's volatile. There's no guarantee at all. Or atomic, I have to, if I want to persist that data, I have to take extra steps to get it from volatile memory to some persistent media. Right, so the use of memory map files is also in the model. Now, this has been well known for volatile memory for a long time, mmap and its friends, right? But for persistent memory, it's a little different. Because again, when you memory map a file into a PM virtual address space, you are now persisting that data. Right, so you don't have to flush it or take care of synchronization or whatever. So it's a little bit different model. And the camera. Right, so again, it's a programming model, not an API. Right? Nope. So it has four modes, right? Conveniently arranged in a quadrant. Isn't that special? Right? So there's block mode, right? And from a user point of view,
that's a magical quadrant.
Magical quadrant. It has magical characteristics. Let's say that. So there's a file area and there's a block area. Right? So again, this is storage semantic, very familiar stuff. Right? So it looks like a disk. NVDIMMs can be used, and they are disk-like because you're accessing them by block storage semantics. So that's two parts of it. That's the I/O area of the quadrant, and then the persistent memory area of the quadrant is, you can see the same thing, file, and then we have volume, instead of block because it really is byte addressable, so the concept of blocks is now an abstraction rather than something meaningful. And the media type is memory, and the NVDIMMs that we'll talk about in a little bit are memory-like. In other words, they are accessed via memory CPU load store semantics, right? So those two capabilities are also in the programming model, and you can write code to any or all of those in the same app or the same file system or the same OS, that sort of thing.
Rob, I'm seeing that there's no indication of interface in anything that you're talking about, except that you did mention memory slots.
Right.
Is that not a concern, or is that not a problem?
Well, if in terms of a programming model, as long as I know the semantics on how this particular device is accessed, you can't necessarily see from an application point of view the fine details of a DDR4 memory channel, right? You know there's media there, you know it's represented by a virtual address space, and you know that you can get the CPU to load and store to it. That's about all you know from an application point of view. Now, in the future, there could be, a lot of other physical channels, if you like, that this media is inserted into, right? Which is not part of this talk. It's beyond the scope of what I want to talk about.
Okay, so that is, the interface is beyond the scope.
Right, exactly.
Yeah, because we've heard a lot about NVMe and how you would address individual, NAND chips across,
Yeah, now,
NVMe
let's make one thing perfectly clear. NVMe, in other words, NVM Express, has nothing to do with this. It is a completely different animal. Now, it happens to include the letters NVM, but don't conflate the two. NVM Express is a particular protocol and transport for block devices down a bus. This is not that.
Yeah.
Okay, just so we're clear. Yeah. Good?
So this is not even that on the block mode side.
Has nothing to do with the transport.
Okay.
Right? This is a programming model. Okay, cool. So block and file modes use I/O. Read, write, normal POSIX, right? What are the 5 things in POSIX? You all went to school, right? Open, close, read, write, ioctal. Right? Since 1999, it's been that way. So block and file mode in the programming model are I/O type operations. Yes, sir.
Noticing we go block and we go file, and in my experience, in between the two, we usually have a file system. I'm just curious, when you're talking about the programming model here,
Could very well be.
We're talking about more an
I
object
would
model.
think that if you use file mode I/O, there's probably a file system in the way there somewhere. Right. Absolutely. Okay. And by the way, the authors of file systems can now use this programming model to help them with persistent memory.
I just want to make sure it wasn't a mistake.
You bet. You got it. So you read and write using normal RAM buffers, and the RAM buffers are deposited through block semantics down into a device, and life is good, right? Volume and persistent memory mode, however, enable CPU load store. And again, there's been a number of companies that are already implementing this. So instead of reading and writing RAM buffers to a peripheral, we are now using the CPU to load store in and out of registers into memory. Full stop. Right? So the processor has to make the software wait.
Could you go back a slide to the magic quadrant again? So in persistent memory mode, right?
Right.
There's a file at the user level, or at the kernel protected level, there's volume. Now go up a slide, and you call about volume and PM modes.
Yeah, volume, the PM mode for file or volume, the same way. That's it. It might be a little bit of a typo.
You're not using the. Okay.
I get it.
I'm just trying to understand where you're going with this.
Yeah.
It gets even muddier later.
Yeah.
Oh, good. Excellent.
It gets worse?
I was told there would be no math. Yes, there is math. I got news for you, right? So this is about writing code. So let's talk about I/O. This is very familiar. We've all done it all our lives, right?
There's my file system.
Sometimes fast, sometimes not. But block and file mode. The block mode is targeted for a layer that a file system writer, for example, or a blockware application would use. How do I get my nice file text unstructured data into a block of storage, right? And there are atomic writes, just like all file systems tend to do, right? And also in the model, there is thin provisioning management capability built in. So if you, as the application or file system writer, want to take advantage of that, you can. It's in the model. And then, so block mode, again, file mode, strictly for file-based apps. You can discover and use atomic write features, so you're depending on the underlying layer to provide atomic writes for you.
I think we're going to run into the same problem
Right?
here.
Thin
this is
provisioning
I/O.
is not really, a block device sort of characteristic. I have thin provisioning on a DAS device.
Right.
I have thin
So if
provisioning
I
at
have
system
a
level.
persistent memory device that's being used in NVM.block mode, you think you have a block device, and your program accesses it as such.
But thin provisioning says something like at some
So
point
I want a
run out
model
of
where I
space.
create 100 gig space, and I'm only using 2 of it, and I only provision 2 of it, just like you would do the same on a regular.
But thin provisioning, I can
rotating
actually
disk.
run out of space. With a device, you typically don't run out of space.
Hey, all these devices have finite physical size, right?
Even though they're thinly provisioned.
No, that's right. So just like we have thin provision management for other devices that are persistent but are not memory, aka disks, right? We have the same thing here. And then file mode. So that's file mode. This is normal I/O. Looks very familiar.
I'm just coming back to my preoccupation with file systems. Is there really an NVM file mode? From my point of view, usually a file mode would be addressing the file system. The application isn't talking to the NVM layer.
Oh,
It's
no,
the file system's
exactly. So you're
responsibility.
file-based in normal I/O mode here,
Right.
which is one of the 4 things in the model. I have a file-based app. There are extensions for this file mode, so it understands how to deal with persistent memory. And now here's your file system. And it's talking to a block device just like it normally does.
But that would mean that the extensions are something that have to be baked into the file system
Correct.
in order to be aware of
Correct.
this. Okay.
Just like same way with the block device driver, you have to bake in these extensions
Wouldn't you think the
to have the
extensions
block
would be
device
below
be
the
in
file
persistent
system?
memory.
Thank you. That's where I was
Sorry,
going
Ray?
with that.
Wouldn't you think the extensions would be below the file systems
Nope.
rather than above the file system?
Nope. It has to be aware of certain things like how to do an atomic write. So here's persistent memory mode. This is actually simpler, right? This is a simpler model, right? So again, I have volume mode, which is a software abstraction, right? Address ranges, in other words, virtual address range. Here's my first range, here's my second range, right? And then again, because it's a volume mode, but it's actually accessing memory directly, this has thin provision and management. And then there is a persistent memory file mode. Again, this is mostly used for memory mapping files into persistent memory regions, right?
But again-
Memory mapping files into PM regions.
can I-
Go ahead.
The programming model, do we need one for the files? Because basically all we need is a file system that is where, like, this next slide is perfect. No, the next slide is perfect because it says PM aware file systems.
Right.
For me, that's where all that smart, the model, when I
bet.
get up to the programmer at the file level, he shouldn't really care because he's addressing a file system that has done all that heavy lifting.
Right.
I can totally
And
get it on the block.
As long
volume
as
part.
this file system, and again, there are commercial implementations of these things as well as implementations in, academia and whatnot. As long as they are persistent memory aware and know that they are accessing this device, which is a memory device,
Exactly.
not a block device, then if your application understands that, oh, I have a PM-aware file system which can talk to a PM device, now I want to put code in my app to leverage that as opposed to a garden variety file system, which is not aware of persistent memory.
Okay, and you're going to tell us why that's more important later.
Yep.
Okay.
And then again, so you can see the operations. Now the application, if it's PM aware, can, if it wants to, directly access the memory. Again, it's just a memory range. But it has to be aware that this is a persistent memory range as opposed to a non-persistent or volatile memory range. Right? Because when you fire up an app, normally you think, oh, I'm going to go out and mmap and here's my address range and everything's cool and I can address it virtually and I'm talking to DRAM and the power goes out and poof.
How does virtual memory interface with this model?
So a virtual memory is the address space for a given app, and if it's aware that it has persistent memory as an address space as opposed to the address range for non-persistent memory, right? There are now 2 address ranges that applications must be aware of if they intend to use this model, right? Because I could read and write the volatile DRAM, right, with my normal program, and then here's this address range which has been passed up to me and I am made aware of it. And I want to map a file into the PM range, And now when I do my memory mapping, I'm persisting that data
The
instead
address
of
ranges
being
don't
DRAM.
don't overlap. I mean, I couldn't have the same address, which would be persistent
Well, it's
memory.
a virtual address range as given to you by the processor and as seen by the BIOS, et cetera, et cetera.
But the physical address range doesn't overlap.
Physical address range doesn't overlap. Right. Can't. Because these are not in the same DIMM slot.
You mentioned two address ranges, and I'm thinking, there's different ways of
Right.
defining.
So if I'm writing a C code and I malloc some memory, I'm going to get volatile memory. And the kernel's going to go, oh, Rob, you want a malloc 4K? Sure. Here's the address range. Here's your pointer. That's the start of your range. You got 4K. Go. Right? Well, there is a way now in the programming model to malloc an area of persistent memory. And the kernel says, oh, Rob, you just malloc for persistent memory. Great. Here's your virtual address start. You got 4K. Go.
Unless it specifically requests persistent memory,
Bingo.
like an older application
Has to
would
know
not be
the
able to ask
difference.
for it.
Has to know the difference.
So
That's right. Because now I got two
non-persistent
forms of memory hiding in my machine. I got a PM device and I got a not so PM device. Okay, so map and sync. This is where it gets fun, right? There is math, right? So again, I'm associating the mapping function, very straightforward, been done for a long time. I'm associating a memory address with an open file. Right? The memory has some people like the term backing store. It has a backing store. So the system is trying to guarantee to me that my mapping to this thing eventually makes its way to the backing store. Well, again, the difference with persistent memory is as soon as you map that in the CPU stores, it is persisted by definition. This is a great thing. And so you can request a specific address, which is what map does. Now, sync, on the other hand, is interesting, right? Because flushing CPU caches is an interesting little twist, right? Because again, there's 3 levels of memory at current inside most popular CPUs. And by the way, memory tidbit for you, those are SRAM caches, not DRAM. Yet another different form of memory. Okay? So CPUs today can hold a considerable amount of data inside their own caches, which is not on the devices in the memory bus. So the CPUs have to figure out when to flush their cache. And there's all sorts of interesting instructions that you can tell the CPUs to do this and immediately flush all the way down to what they think is a memory range. In other words, get rid of all my data in all my cache lines and flush it out.
Now, we said there were 2 address spaces earlier because we're going to have DRAM and
Correct.
persistent memory.
Right.
Does the CPU differentiate?
It has to.
Okay, so it knows
If it doesn't,
internally.
you are hosed.
Well, yeah, that's where I was going with this.
Because Murphy says you're going to write to the wrong place.
And
So
in that
yes,
case-
it is well aware of 2 different ranges. You bet.
And so it's still sharing L2, L3 for ultimate destination,
Yep.
1 or more.
Yep.
Okay.
Exactly. Hence the programming model.
Exactly. Okay.
Right.
Good.
So now, again, just because you sync doesn't guarantee order. And persistence has a funny, wonderful relationship with order. Right? So if you want to guarantee order, you have to take some, guarantees in your program, and you have to look, to the CPU to say, yep, okay, all cache flush all done. Right? And in what order? Because these things have a lot of cache lines, and you don't have any guarantee about cache line 1 syncing before cache line 52. Right? That's not visible to the application. So there is this fun stuff about looking at if your application really wants to be order consistent,
Rob.
you have to take care.
The order for cache line 1 and cache line 52, if they're to the same address range, is a challenge. I mean, it can't be.
No,
the same
they're not.
They got to be different address ranges.
Right.
So you're saying the ordering between those different address ranges could not necessarily be guaranteed.
Right. That's right. So you have to take care of that. Right? Now you know why file systems back in the day were hard, and they still are. Because order is a tricky thing. Okay. So some pointers for you, pun intended. Right? So if I've got a memory map data structure in persistent memory, how can one refer to the other? How does that work? Well, guess what? You got 2 ways to do it. You can use the virtual address as a pointer, just like you do in volatile memory. Right? And then you can assume it will get the same address every time it's memory mapped, right? Now, you have to manage that as you got your volatile space and your non-volatile space, right? Or you can use base plus offset, which is even more time tested. This is the way that real memory machines worked for decades, right? I have a base address, and now my range becomes an offset. right? So it could be the start of a memory map file. That's pretty convenient, right? So the pointer would include the reference to that namespace. I've got base plus offset, right? Makes sense. Okay, so atomicity.
But the virtual address
Yeah.
for a persistent memory
Right.
could effectively change. I mean,
That was making me
It's
ask
up
the
to the
question.
kernel.
What happens?
It's a virtual address. It's up to the
we're-
kernel. The kernel is doing paging. Remember how kernels work, right? Page table, bring data in.
worse
So,
than
but
that,
if
what
it's a
happens-
Same
page-
process with persistent memory.
it's
No
page-
different, but a different range. It's two completely different worlds, and the kernel has to manage it, and if you intend to map stuff to it, you have to manage it too.
Which brings me to my next question is, memory is lovely because it was non-volatile. So when I shut my server down and I swapped my SIMs and moved my slots or added new ones, I could boot it up and it would look around and find out what happens when I'm in a persistent model.
That's a physical address thing,
That's what I thought.
right?
So
So
if I
you
added-
have this funny thing called a CPU in the middle.
Oh, okay.
And you also have BIOS, but this isn't a talk about BIOS. It gets more fun. Right.
Okay.
so a page can be either persistent or not.
That's correct. You got it. Because I've got two
And not only that,
memory spaces. Isn't this fun, Ray?
no, it's not. It's not fun.
That's why we're doing a programming model, so we can help people do this stuff. Because it's not intuitive.
Okay.
Right? It's like, oh, my brain hurts. I got two memory. What? No. So this is part of why we do it. But failure atomicity is, unfortunately, if you like, it's processor specific. Right? What happens when memory location XYZ all of a sudden gives up the ghost and the CPU waits and waits and waits, and then it does a machine check. It doesn't return you an error code like SCSI does. SCSI gives you these nice little things called cents, right? We've known that for years. There ain't no sense in this. Just kidding, right? But you do get an interrupt and a machine check. It's like, oh, crap, memory location, no good. And you have to deal with this as a programmer, right? Because there is no SCSI retry going on here, right? So you get exceptions instead of status. This is again, you think of memory, you get exceptions. You think of I/O on a SCSI or NVMe, you get status coming back, right? So this is, again, there will not be a test on this, but Linux machine check error from a persistent memory aware file system, I have to be able to deal with that. And this is Mr. Kernel down here trying to deal with this. Right? Your application may not know. It can use a native file API, or again, if it's PM aware, it can use load store directly to and from, but the machine check is going to interrupt and the kernel is going to handle it. So this is where the OS vendors come in.
keep saying PM aware. I can do a load store at any physical address in a system anytime I want, whether it's
No,
PM
no,
in
you
there or
can't.
not.
You can do it to a virtual address. You ain't writing physical address code unless you're down here.
Okay, I can do a load store to any virtual address in the system whenever I want.
Correct.
Whether that page is virtual, is persistent or not, I
have to be
do that-
aware.
I can still do that load store without being aware.
Well, you can. You're flipping the dice. This is a new world, Ray. I got two areas of memory, not one. One's persistent, one's not. Deal with it. Just kidding. So here's the NVM programming twig, the technical working group. This is work in progress stuff. So we're writing a white paper about atomicity, right, and transactional persistent memory libraries. That's a fun thing, right? And entire libraries of code which deal with persistent memory and how do you transact, in other words, you've all heard of ACID guarantees, right? How does that work with persistent memory in the face of a potential machine check, for example? And then remote access, right? This is another one. You know, how do I make persistent memory more highly available? Maybe by doing RDMA techniques. We've been doing this in storage for quite some time, right? Can we do it with memory? Or maybe have volatile memory RDMA into a non-volatile memory or persistent memory, right? So this is kernel level work going on down here. Up here, for the data structures and whatnot, this is user level work. So what we're trying to do, again, long story short, is align the programming model with what the industry wants to consume. They want to know how to use this stuff, right? Some of the SNIA members are manufacturing this. semiconductor manufacturers, some of the SNIA members, and lots of OS companies, Tom's on the phone from Microsoft, are doing this from that level. There are entire companies wrapped around with file systems trying to understand how to use persistent memory as part of their file system offering. So all the way up and down, right? But we don't want to force a specific API. This is not a mandated API. This is a model on how to program for this kind of media. So what are we doing it? We're exposing, again, we have 4 different models of it. There are also, variants that are using this technique, the Linux PMFS code. Look it up on GitHub. PMEM, which is, again, persistent memory. There's a whole flock of examples in a PMEM.io library that the Linux community has started to write. And again, this is pulled down from GitHub. But this is really interesting, right? These memory technologies are, arguably in their first days, weeks, years, right? The cost of this stuff will come down over time. No mistake about it, right? So as that cost comes down and new emerging technologies, different forms of persistent memory come up, right? There's going to be an increased amount of work in this area. No question about it.
You consider something, I'll mention a technology, NVDIMMs as a persistent memory?
Yeah, stay tuned, right? So this is kind of the horizons where we've been on. Until recently, we've been doing this, right? Look familiar? Now we want PM middleware, so file system aware of persistent memory, and then entire libraries so applications can make library calls, right? One level removed, and then finally into languages. We think one of the last horizons, or maybe, certainly after this, is to make compilers themselves aware of what's going on with persistent memory.